And now, from IBM, Mark Squianti.
Thank you, Ellen, and we would like to thank the entire Wagner Judging Committee for this opportunity to present our work on the Mark, an integrated stochastic resource planning of human capital supply chains. The services sector experienced enormous growth over the last 2 decades. Governments, healthcare, information technology, finance, and insurance, just to name a few examples. Critically important to these industries and central to the notion of services are the concepts of people, talent, and skills, or in other words, human capital. The ability to have the right people with the right skills in the right place at the right time is the critical driver of success, growth, and client satisfaction in these industries. Our services organization considered in this work is IBM Integrated Technology Services. IBM ITS is one of the leading IT support organizations in the marketplace, specializing in a wide range of service and service products. In 2007, ITS partnered with IBM Research to develop novel solutions that advance the way ITS manages and plans its human capital, thus helping to differentiate ITS in the marketplace. ITS was trying to address several key questions at the time, examples of which are: how can we reliably forecast demand in terms of revenue, in terms of the number of engagements, and the skills needed to deliver on these engagements? Do we have the right skill levels to satisfy demand and meet our business objectives? What kind of hiring, training, and career management policies will better align our skill composition with our business objectives? Not having answers to these questions led to our collaboration with ITS to address them, which in turn led to the development of OnTheMark. In today's presentation, we will first motivate this work in a bit more detail, followed by a high-level overview of OTM and its capabilities. Then we will present a somewhat deeper dive on 2 of the technical areas, in particular risk-based capacity planning and supply evolution and optimization. We will conclude with examples and statements from the successful worldwide IBM deployment of OTM. Demand, supply, capacity levels, these concepts are so well studied in supply chain management practice. Our motivation is the fact that such common supply chain concepts do not directly translate to human capital management. People simply are not parts or perishables. We are prone to incentives. We suffer from burnouts, underutilization. We learn, we acquire new skills, we evolve over time in our careers. In the context of the ITS business problem, human talent represents a long-term capital investment. IT worker productivity and efficiency depends upon workload and utilization. And they are capable of deploying multiple skills at the same time across multiple engagements. Hence, new operations research models and methods are required to address these complexities. Here we see a high-level overview of OTM. This framework supports an end-to-end process. One of the key contributions of this work is that it develops and integrates innovative models and methods from across a broad spectrum of areas within operations research. Our overall objective is effective human capital management. The partitioning of the overall problem into the components illustrated in the diagram is in great part based on business and organizational aspects of ITS and their human capital supply chain. In fact, each capability is used independently by different organizations across ITS to support the various business processes. A key point is that the OTM methodology has been developed, implemented, and successfully deployed within IBM and is having important impact in practice. OTM starts with skill demand forecasting, for which we have developed win probability models that analyze market opportunity data and predict how many of the opportunities will turn into actual engagements and when they will start. To link these forecasts with skill requirements, we need bills of skills, which are the equivalent of bills of material in classical supply chains. These templates, which describe how each type of engagement should be staffed, are derived by applying machine learning and clustering techniques to historical project information and then used to translate engagement level forecasts into skill requirements. The next component of OTM, risk-based capacity planning, concerns the need to determine the capacity levels for people skills that best satisfy the forecasted demand while also maximizing performance. This capability addresses the revenue cost dynamics and trade-offs between the risk of having insufficient people to deliver an engagement and the risks of having too many underutilized people, both resulting in losses to the business. Business performance here is a function of the cost of maintaining skill capacity levels and the revenues for service engagement delivery, where the latter is discounted by engagements at risk of being lost due to insufficient capacity. Another characteristic of human capital supply chain concerns the significant and complex time-varying dynamics on the supply side, with many people acquiring skills, changing roles, some people leaving, and new people being hired. The supply evolution and optimization capability concerns the modeling and analysis of future skill supply, taking into account hiring, training, and attrition. This capability first models the future skill composition over time and then solves a corresponding optimization problem to determine the future evolution of human capital supply and the skill composition through available investments in order to maximize performance over time. At this point in the end-to-end process, we have obtained the skill capacity demand targets and the skill supply estimates. Unlike resources providing only a single function in traditional supply chain, the ability of people to perform multiple functions requires advanced forms of matching the expected multi-skill supply against the supply-demand targets. The OTM multi-skill shortage and overage optimization addresses this requirement by minimizing a weighted sum of the skill shortages and overages over all skills. We solve the resulting optimization problem through a combination of linear programming and dynamic programming. Now let us turn to risk-based capacity planning in more detail. Recall that our goal here is to determine the capacity levels for people skills to best satisfy demand while addressing the trade-offs associated with revenue, cost, and related risks. To highlight the difficulty of this problem, consider a simple scenario in which we have a forecast for 10 engagements over the next quarter. The best number of people required to deliver that set of engagements depends upon the degree of overlap among the delivery time processes for these different engagements. A model of these complex dynamics and stochastic net behaviors is needed to appropriately determine the skill capacity levels to maximize performance over large sets of engagements and skills. Our mathematical model of capacity planning is a stochastic loss network. Stochastic loss networks consist of a set of skills, each of which has a certain capacity level, and a set of engagements, each of which require capacities across a subset of the skills. Then the stochastic system dynamics proceed as follows. If there is sufficient capacity available for each skill at the point in time when the engagement needs to be delivered, then the engagement is delivered, and the skills are reserved for the duration of that delivery time, and the revenue associated with the engagement is realized by the business. Otherwise, due to an insufficient capacity in at least one of the required skills, the opportunity to deliver the engagement is at risk of being lost, and so too is the revenue associated with that engagement. We therefore can express the expected realized revenue as the difference between the expected demand revenue and the expected revenue at risk of being lost. Now, a primary reason why we took this risk-based approach is that it is not uncommon in the services industry for customers to switch to a competitor or withdraw the engagement if the service cannot be delivered at the required time of delivery. Hence, it was critical to model this certain aspect of the services industry. Now, stochastic loss networks have a long history in some application areas, in particular telephony. However, they are not widely used in practice to great extent because it is difficult to calculate solutions for these models. One of our contributions is to develop a new set of approximations and results that address these problems for our particular application domain. While the stochastic loss network is used to model the dynamics and the complexities of the capacity planning problem, our overall objective is to determine the skill capacity levels C that maximize expected profit in terms of the realized revenue summed over all engagement types, and the people costs for maintaining these skill capacity levels, where those costs include various investments to achieve those levels. In this formulation, the loss network captures sources of uncertainty and relationships among demand, supply, and loss risk probabilities. To clarify the exposition, let us consider a simple example comprised of 2 types of engagements and 3 types of skills. The delivery of an application development engagement requires 4 Java programmers and 2 engagement managers. Similarly, a data administration engagement requires 2 database specialists and 1 engagement manager. Both of these requirements are provided in the A matrix. It is important to note that the delivery of each engagement involves simultaneous allocation of the skill capacities. It is also important to note that the general notion of arrivals in stochastic loss networks is used for our purposes here to model the points in time at which the engagement needs to be delivered. As this differs somewhat from the common usage, we emphasize that the arrival process for each type of engagement identifies these points in times when an engagement needs to be delivered. We will initially assume in what I'm about to describe that these processes are Poisson processes, and then we will briefly summarize our corresponding results for more general renewal arrival processes. To study this model, let us first consider the multidimensional stochastic process N of t of the number of active engagements at time t. This process is defined over the state space S of all possible values for the number of engagements of type 1 and type 2. With no capacity constraints across both dimensions, its stationary distribution pi is known to be a multivariate Poisson distribution with parameters nu1 and nu2, where nu1 is the arrival rate for the first engagement type and nu2 for the second engagement type. And here, pi represents the stationary distribution pi represents the limiting probability of the system being in the state n1 and 2. The multidimensional stochastic process of interest for our purposes, however, is the stochastic loss model that is defined over the exact same state space, constrained by the capacity vector C1, C2, and C3, which yields the polytope S of C. G of C here provides the total probability mass of this polytope. Then the stationary distribution pi of our Erlang loss model has a product form solution normalized by the partition function G of C. The loss risk probability L sub k for engagements of type k can be computed as a function of this stationary distribution pi. Turning to the general problem, the Erlang loss model can be more formally expressed in very similar terms to our illustrative 2x3 example. In particular, equation 1 listed here expresses the product form solution for the stationary distribution. Equation 2 expresses the normalizing constant. And the loss risk probability L sub k is computed as a function of the stationary distribution and model parameters. Unfortunately, even though we have an exact product form solution, the computation of the normalizing constant G of C is known to be sharp P complete, which is harder than NP complete. A few approximations have been proposed to address this computational complexity, most notably the Erlang fixed point approximation. However, we found these approximations to have serious accuracy problems in the networks parameterized by real-world ITS data, as part of this project. We therefore set out to obtain a family of better approximations. Since the stochastic loss probabilities are functions of the stationary probabilities for each point in the polytope S of C, and given the computational complexities of computing all of these probabilities, we approximate the stationary probabilities for the set of points on each of the lines highlighted in the diagram by the stationary probability for just the single point in that set that has maximum probability. This mode of the set of points in the polytope can be efficiently obtained as the solution of a primal dual problem. And then, of course, the stationary loss risk probability is computed as a function of the stationary distribution approximated in this manner. Given the time constraints, we summarize our main mathematical contributions in the area of risk-based capacity planning as follows. Under Poisson arrivals, we prove asymptotic exactness and strict dominance of our approximation methods. We also derive important results for the feasible region of nonlinear Erlang loss model optimization problems, and we exploit these results to obtain in order to efficiently solve these optimization problems or compute solutions to these optimization problems. We also developed an analogous set of approximation methods under general renewal arrival processes, and in this case we establish a set of results that are completely analogous to what I've just summarized for the Erlang loss model. Let's consider a simple business case of applying risk-based stochastic capacity planning. On the y-axis, we show profit, revenue, and cost, and on the x-axis, we show different loss risk tolerances. The set of results to the far left provide the results for the solution in which profit is maximized. As we move to the right and constrain the risk tolerances, we're satisfying more and more of the demand, to the point that at the far right, where most of the demand is being satisfied. The key point here is that as you move to the right and satisfy more of the demand, the revenue is indeed increasing. But the cost is also increasing, and it's increasing at a faster rate. As this illustrative example shows, the risk-based capacity planning capability provides executives the ability to determine how they want to operate their business in terms of maximizing profits, addressing revenue cost issues, addressing risk probabilities and risk tolerances, as well as other business concerns. Now let us turn to consider supply evolution and optimization in more detail. Recall that our goal here is to understand how the skill composition of people will dynamically evolve over time and determine the best possible actions to adjust these evolutionary dynamics to maximize performance. As an example, in the military, it takes a long time for someone to reach the level of a general. Steps need to be taken at all levels of this human capital supply chain, including recruiting, training, experience, and promotions, in order to ensure that there is enough talent at all levels, with lower levels feeding upper levels over time. A model of these complex dynamics and stochastic behaviors is needed to appropriately determine the future skill composition of people to maximize performance. Our stochastic supply evolution model is based on aggregating people according to various attributes of human capital groups. Examples of the type of attributes we're talking about are skills, proficiency levels, and the like. So we're taking the people and we're aggregating them into groups based on these attributes. There are dynamic transitions among these groups, including both internal and external transitions. These dynamic transitions among groups lead to a very complex network topology. Consider the simple example that is illustrated, comprised of groups for human capital groups for C, Java, and SQL programmers and engagement managers. And consider the evolution among these groups that occurs over a given period of time. With some probability, people are hired into each of these groups or are treated out of these groups. Similarly, there are transitions from one state to another state with certain probabilities. We exploit the properties of this network topology for scalable supply evolution solutions. One example of this is the use of sparse matrix methods because transitions tend to be relatively local. Reward and cost functions are associated with each group. The reward or cost for each group is a function of the number of people in the group and the amount of time that they spend in the group. For example, revenues for delivering engagements. Reward and cost functions are also associated with group transitions. The reward cost for transitions from one group to another is a function of the groups involved and the number of people that take that transition. An example would be the cost for retraining from one group to another group. Available actions that can be taken with respect to any of the group transitions, such as hiring, may also have lead times that capture the delays between when you initiate the hiring action and when the new employee comes on board. Reward and cost Once we have these models and we've grouped the workforce into the different groups, or aggregated them into the different groups, we then can determine the evolutionary path and the future composition of the capital network. If you will, if the policies continue as they have in the past, we can look at how the workforce evolves over time. Similarly, we could look at what happens if we change those policies, how that would affect the evolution of the human capital network. Then what we can also do is look at what actions can be taken in terms of hiring, in terms of adjusting the training and the internal transitions to have the workforce evolve in such a manner so as to maximize business performance. Our stochastic supply evolution model is a discrete time, multidimensional stochastic process that records the number of people in each human capital group. Consider at the current time t equals 0, we know with certainty that we have a head count of 100 managers, looking at the upper part of the chart. In the next time period, the state space of the discrete time stochastic process needs to allow for all possible head counts within the manager group, governed by the set of transition probabilities as shown in the diagram. Expanding the view for all possible populations for that particular group, as well as considering all possible groups, we clearly have a prohibitive cursive dimensionality problem as the state space blows up. To address this problem, we consider instead a decomposition of the discrete time stochastic process that records the expected number of people in each group over time, as shown in the lower part of this chart. In this case, we have a single state for each group and an analogous set of probability matrices that govern the transitions from one state to another within each time interval. More formally, and focusing on the first line, we express in expectation the number of people in state I at time t plus 1 equal to the number of people at time t plus the number of people hired plus the number of people transitioning into the state from other states, minus the number of people transitioning out of this state, either to other states or through attrition. This can be written in one of two matrix forms, depending upon whether you're forecasting the expected number of hires or the probability of hires. Then straightforward calculations yield the final skill composition at the end of the planning horizon, as shown in the final formula here. But while our discrete time stochastic process is used to model the dynamics and complexities of the supply chain evolution problem, our overall objective, is to determine the best actions that maximize expected profit summed over all time periods, where revenue depends upon demand and costs include maintaining the skill capacity levels as well as various investments to achieve these levels. Note that adjusting the transition probabilities as part of the optimization problem, it represents actions such as training. Now, to efficiently solve this optimization problem, we stack the summation in the objective, together with the corresponding linear dynamical system constraints, into a linear program with respect to the decision and cost vectors z of w, as noted on the chart. In addition to the dynamical system constraints, we also have various constraints such as balancing total flow, limiting total outflow, limiting total attrition, and restricting revenue to not exceed demand, each of which can be written in a similar matrix form. Finally, upon completing all of these derivations, we reach the complete specification of our LP formulation, which can be efficiently computed. Now let us briefly consider a representative business case using supply evolution and optimization. We start with the evolution of a single skill based on historical forecasts. We observe the prediction of a significant increase in attrition in November and December due to baby boomer retirements. Adding the demand forecast for this skill, we observe that there will be a significant shortage in the skill relative to demand due to these retirements. Next, consider the possibility of incentivizing some of this attrition to postpone retirement until people with the skill can be brought on board. The higher the incentives, the larger the fraction of people who are willing to postpone retirement with diminishing returns. In this business case, the supply evolution optimization determines the best set of investments to maximize profit against forecasted demand, as shown in red. Many organizations would never realize the upcoming shortage due to future retirements, and thus they would lose considerable revenue while trying to catch up over the hiring lead time, as shown in green. Some organizations might realize the upcoming shortage, but they will hire enough people to fill the shortage as known in September, and therefore not understand the transition in this state will occur naturally over time, thus hiring too many people and creating a future overage problem, as shown in blue. Lastly, let us turn to summarize our experience with the deployment of OTM within IBM. The OTM integrated suite of OR models and methods has been implemented and deployed around the world to support the management and planning of major portions of the ITS human capital supply chain. Our experience with the worldwide deployment over the past couple of years has been very successful with significant benefits to the ITS business. The OTM suite serves as a central information and analytics base for all organizational and business users within ITS. The OTM suite provides an automated solution that allows for quick updates and rerunning of the OR models and methods in real time as conditions change. Quarterly reviews have been performed to track and evaluate the accuracy and business impact of OTM solution methodology. Overall, demand forecasting accuracy has been found to be within 90%, above 90%, relative to revenue targets. The relative errors in the loss risk probability predictions in comparison with data on real-world engagement losses have been found to be within a few percentage points. And the accuracy of our supply evolution modeling capability has also been within a few percentage points in estimating the skill compositions of organizations on the orders of thousands and larger for 6 months up to a year. Various business cases, including those described in the paper, have demonstrated the significant benefits of our OR models and methods over the methods and approaches used previously in ITS. Quarterly reviews with ITS executives over the past couple of years further demonstrated the significant business impact of OTM. In fact, as part of the initial quarterly review with IBM executives, business impact comparisons demonstrated the cost revenue benefits of OTM in the first quarter to be above $11 million in the US alone. Similar results have been obtained as part of the worldwide OTM deployment over the past couple of years, during which our findings of business impact studies demonstrated the combined revenue cost benefit of OTM to be commensurate with 2 to 4% of the ITS quarterly revenue targets. And the use of the OTM framework and methodology in broader application settings in support of future IBM products and service offerings in the marketplace and beyond IT services continues as an ongoing effort. To complement our perspective on the successful deployment of OTM within IBM, which is described in more detail in the paper, we would like to share with you some statements and testimonials from executives and colleagues across IBM involved in OTM deployment and productization.
As many of you may know, IBM has changed its business model from being a company that was dominant in the hardware space to one that is now also dominant in the services and software space. So in a knowledge economy, it's all about the talent, the skills, putting them in the right places, putting them on the right tasks to serve clients and to make sure we're serving our shareholders too.
There's no doubt that businesses and organizations in all industries are in need of better and more sophisticated tools to help in their talent management challenges. Following tactical investments in HR and ERP systems, companies are now in a position to use their enterprise data, coupled with advanced analytics, to pursue more strategic, personnel-driven improvements.
The Inform's audience does not have to be convinced of the importance of supply chain in modern business and industry. This is an area where OR has been effectively practiced and has contributed to significant operational and financial improvements in businesses and organizations worldwide. Another vital component of an organization is its workforce, or in other words, its human capital supply chain. A productive, skilled, and ultimately happy workforce is key to an enterprise's success. Human resources, individuals, are far more complex to model than machines and parts. So traditional supply chain models do not translate directly to human capital management. Concepts such as hiring, training, compensation, incentives, acquisition of new skills, and perceived fairness in treatment must be considered in human capital management models. These concepts impose new requirements in optimization-based models. New algorithms are often required to deal with these complexities. Human capital management is an area of operations research with incredible potential for new contributions. The IBM team has made significant progress in designing and deploying the OnTheMark analytics suite. There is much more to be done, and we are eager to lead research and deployment activity in this new direction.
The team worked on a problem related to a business that was a little over $1 billion in revenue, which means about $300 million of revenue per quarter. They were able to achieve improvements in performance of a few percent, which is a few tens of millions per quarter. Now, in the context of IBM overall, why this is significant is more than 30 or 40 billion of our revenue comes from services. So I think the OnTheMark team has done a remarkable job in using math to solve these business problems, and I look forward to continued impact both for IBM and in the service of clients as IBM takes some of these ideas out in the service of what we need to do for them.
As a technical executive at IBM, I am seeing more and more clients interested in investing in advanced workforce analytics and looking for novel solutions such as OnTheMark to help optimize their workforce to yield greater business value.
We're being able to take these high-quality, high-performing research assets such as OnTheMark and be able to bundle them with our workforce software products, taking that to market to be able to deliver compelling value for our clients. We are very excited by the response that we're getting in the market.
One of the opportunities we are especially excited about is in the healthcare sector. As we expect more and more people to come under the insured umbrella, the need for long-term training and staffing plans to accommodate the increased demand for healthcare skills and their optimal deployment is vital. And it will take more than a back-of-the-envelope calculation to figure out how many to train, where to deploy them, and what skills to impart.
Thank you.